Okay, so in this video, we are going to look at the concept of differentials. We'll first look at the definition, a few examples of how we compute differentials, and then we'll look at what it actually represents geometrically. So suppose we start with a function of x, and as you will see, if you change the independent variable, it doesn't really change much. Suppose we have a function of x, so y equals f of x. We can find the derivative of y with respect to x because y is a function of x. So dy over dx is just the derivative of the function with respect to x. So this is f prime of x. And all the differential is the dy. If you remember, the Greek letter delta stands for change, but the Greek letter delta is just a d. So this means change in y over the change in x, right? This is the slope of the tangent line. So the change in y over the change in x is the derivative, the slope of the tangent line. If all we want is the change in y, dy, multiplied by dx, and so dy will simply be f prime of x times dx, the change in x. And dy is called the differential of the function. That's what the differential is. The change in y is the derivative times the change in x. But always think of it as just differentiate the function, dy over dx, that's f prime. The differential is just the change in y, dy, so multiply across by dx, and so dy is f prime of x times dx. If you prefer, you can write this as dy is dy over dx times dx, and then it makes the equality even more apparent. The differential dy is the derivative of the function dy over dx times the change in x dx. Then it's really obvious, right? Because dy over dx times dx, these two cancel, and you're left with dy, the change in y. You could ask, well, what if we had the function of, let's say, t instead of a function of x, and what would be the differential, right? Well, if y was a function of t, you would differentiate y with respect to the independent variable t, so it'd be just dy over dt, and that's f prime of t. The differential always is just a change in y, so multiply across by dt, so dy is simply f prime of t dt, and once again you have the differential. Of course, if you wanted, you could say this is the same as, well, f prime of t is dy over dt times dt. And once again, this is clear if you just think of it as change in y over change in t times change in t. If you cancel, you're left with the change in y. And this would go the same if you had a function of u, v, z, or any other variable. So let's do some examples. So the question will be, in the following problems, for each function, y, find the differential of the function. So what if we have a function that is a function of x? And say the function is sine of x cubed. Well, the differential dy is the derivative with respect to x, because the function here is a function of x, times dx. And again, that is just a differential. The change in y is the change in y over the change in x times the change in x. And dy over dx is the derivative of the function. So we just differentiate. We have sine of x cubed, we have a composition. The derivative of sine is cosine of x cubed. Chain rule times the derivative of x cubed, which is 3x squared. This takes care of the derivative of y, dy over dx, times dx. And finally, let's rewrite this in the natural order with the simpler terms first and then the more complicated terms. And so the differential of this function is just 3x squared cos of x cubed times dx. And there you have your differential for the function sine of x cubed. What if we had, say, a function of t? So what if y was t squared over 6t plus 1? Well, because now y is a function of t, the differential will be, the change in y, is the derivative of y with respect to t, so dy over dt, times dt, the change in t. Once again, we get the change in y. Well, dy over dt is the derivative of y with respect to t. We have a quotient. We use the quotient rule as always. Derivative of t squared, 2t, times 6t plus 1 minus t squared times the derivative of 6t plus 1, which is 6, over 6t plus 1 all squared. And that's the derivative of y with respect to t, and the whole thing is times dt. We can simplify a bit here, because 2t times 6t is 12t squared, minus 6t squared. So 12t squared minus 6t squared is 6t squared, plus 2t. And finally, we can factor, if you want, a 2t from the numerator, and we'll get 2t times 3t plus 1 over 6t plus 1 squared times dt. And that is your differential dy. So the function is t squared over 6t plus 1, dy, the change in y, is this times the change in t. Let's do a couple more examples. What if we had, say, a function of z? So what if y was 4 to the z to the 5? Now y is a function of z, so the differential of y, the change in y, will be the derivative of y with respect to z times dz. Well, let's differentiate this. Well, what kind of function is this? It is a constant base raised to a function of z. So what we have is an exponential function. The outside function is the power 4, not the power 4, but the exponential function base 4. If you differentiate an exponential function, you get the same thing, times the ln of the base. But that's just the derivative of the exponential function base 4. By the chain rule, we have to multiply what we have so far by the derivative of what's left over, which is z to the 5. And the derivative of z to the 5 with respect to z is 5 z to the 4. There's nothing left over, so we have our dy over dz times, of course, the change in z, dz. As always, we rewrite this with the simplest terms first, then the more complicated terms. The constant terms are ln of 4 and 5, so we'll write 5 ln of 4. Then we have a z to the 4, and a 4 to the z to the 5, times, of course, the change in z. And that is the differential dy. So you see, nothing really new here. All you want is the change in y, and that's the derivative of the function with respect to the variable, in the particular case, times the change in the independent variable. The question is now, what does the differential represent graphically, right? We know that dy is a change in y, dx is a change in dz is a change in z, dt is a change in t, but let's be a bit careful here about the specific meaning of the change in y of the differential. So let's look at function of x. Again, the independent variable doesn't matter. But suppose we have a function of x. Let's just recall that delta is the Greek letter d, which represents change. So this equals change. And the same for d, right? D is just the actual letter d. This is the Greek letter d delta. So d also means change. So if you have, say, a function of x, so y equals f of x, a natural question to ask is, what is the difference between delta y, which means a change in y, and what if we write dy? D also means change, so this also means a change in the y variable. So it looks as if on the surface, these two are the same. Delta y is a change in y, dy is a change in y, so it looks like they're exactly the same. Let's look at a picture that will show us that they're not exactly the same, but they're very close to each other as long as we have a small change in the independent variable. Suppose this is our function. So we have a function of x. Just for argument's sake, suppose the function is increasing, not that it really matters. Suppose it looks like this. Suppose we look at a specific value of x, say here. Well, we know that at this point we have the tangent line to the function, if the function is nice enough. Let's draw a tangent line. And now ask, what if we introduce a change in x? So what if, say, we add to x a change in x? So we'll say x plus, and here there's two letters we could use. We could use dx or delta x. They will be the same change. So suppose we say x plus dx, but this is the same as delta x. So when you have a change in the independent variable, dx and delta x are the same because we choose by what amount we translate x. So dx and delta x are equal. Only because x is the independent variable and we choose the value of our change in the x direction. Let's now look at the change in y and see if there is a difference between delta y and dy. So we have now the value of the function here, and we have the value of the tangent line at that same point. Let's look at the two triangles formed by these 3 points. We have this one, and we have the bigger one with the value on the function. This is just your tangent line, so this is the y value on the tangent line. But we also have this. So let's see. Delta y is the exact change in y. And this is what you'll see as the difference between delta y and dy. This is the exact change in y. Look at the picture. We've changed x from here to here, and y has changed from this value all the way up to this value. So this right here is the change in the function, the exact change, right? We went from the value of y at x on the function to the value of y on the function when x was changed to x plus dx, or x plus delta x. So this is the exact change in the function as x changed from x to x plus dx, and that's delta y. So it's the exact change in the function, the final value on the curve minus the initial value on the curve. What is dy now? Well, let's look at how we computed dy. Let me just move here. By definition of the differential, dy was the derivative of the function at x times the change in x. But recall that the derivative of the function is simply the slope of the tangent line. So what happens? If you take the slope of a line times the change in x, because that's what dx is, it's the change from the initial x value to the terminal x value, right? X plus dx minus x is dx. So that's the change in x. So what if you have a line, as we do here, the tangent line, and you do the slope of the line times the change in x? Well, the slope of a line times the change in x is the slope, not the slope, sorry, but the change in y, right? The slope of the line times the given change in x will give you the change in y of the line. And that's what dy is. So dy is the change in y, but not of the exact function, but the change in y of the tangent line. And that is the difference between delta y and dy. Delta y is the exact change in the function, so the final y value minus the initial y value. But dy, being the slope of the tangent line times the change in x, gives you the change in y, but the change in y of the tangent line. And that's what dy is. One last observation is, if you think of it, well, are dy and delta y close to each other? Well, if you take a very small change in x, say here, look at the picture that you'll get. This will be your dy, the change in the tangent line, and now this will be your delta y, the change in the exact function. And you see that delta y is really close to dy and vice versa. The smaller the x is, the smaller the change in x, the closer the exact change in y in the function and the change in y in the tangent line will be to each other. And that is our conclusion. Because as you move closer and closer to the point of tangency, this point, the tangent line becomes closer and closer to the exact values of the function, right? You see the difference between the tangent line and the function is getting smaller and smaller and smaller as we approach the point of tangency. So for a small enough change in x, the change in the tangent line will be really close to the change in the function. And that's our conclusion. So, and that's the difference between delta y and dy. Delta y, the exact change in the function, dy is the change in the tangent line, but for a small enough change in the independent variable, dy is very close to delta y. So for a small change, delta x, which is the same as dx, we have that delta y, the change in the tangent line in the y direction, will be really close to the exact change in the y delta y, the change in the y direction of the function. And that's the difference between dy and delta y. Delta y is the exact change in the function, dy is the change in the tangent line, both in the y direction. But as we move closer and closer to the point of tangency, delta y and dy are getting closer and closer to each other. In our next video, we will consider an application of the differential, keeping in mind that the differential is the change in the tangent line, and for a small enough change in the independent variable, the change in the tangent line is really close to the exact change in the variable. And we'll consider an application which will be in calculating uncertainties in measurements.